going to talk about some of the Ruby concept that I try to simplify as much as I could, because I think it's very important that we have a good understanding of things. And so this is a cross-section of a Ruby app. You basically have the crust, which is what people see outside, and as you go deeper and deeper, people have less and less understanding of what's going on. And my goal is not to go and talk about really the core and what's going on, how it's made, and why you should use this implementation instead of another implementation. My goal is really to explain why things work the way they are, so we can have a better discussion about the different possibilities and the solutions we could implement. So 90% of our work is done on the surface. We probably all write Ruby code, and we don't all work on different Ruby implementations. And that's totally fine. That's actually really good. That's what Ruby was designed. So we can focus on the core of the application, and we can release business value and make money, which is probably why we have a job. So why should we care, and why should you come and listen to this talk if really that's not so important for us? Well, the reality is, even though you're on top, you need to know what's going on underneath, so you can have an overall understanding, and you can understand when people are arguing and they're saying, well, we should have better concurrency. What does that mean? We need to remove the global lock. Well, what does that mean? Why isn't it removed? Is Matt just somebody who doesn't want to remove the global lock? Is there a reason why we added it in the first place? What's a green thread? What's the difference with a native thread? People told us it's better, but why is it better? So my goal is really to try to explain some of this concept as simple as I can so you can understand the dependencies between each of them. And we're also all craftsmen. We really try to do something we care about. We believe it's almost an art, and we get together. And we want to be motivated by the Ruby spirit. We want to work, and we really want to do something together. And it's interesting because as people are fighting for changes in the Ruby language or in the Ruby implementation, there's a desire for all of us to do a better job. So there's a lot of stuff I won't be covering, and stuff you should know other people are talking about, so I don't really care too much about that, at least for this talk. On the other hand, I will cover a few things that you don't have to know, but it would be good if you know them. So we're going to start at the beginning. We're going to talk about how source code gets parsed to become something, and then it gets executed, and it's all magical. And then we have these C extensions that sometimes we have to use, like Nokogiri or this MySQL gems, and these things that are a bit annoying sometimes, and we'll talk about that and see how they relate to all of that. And then we're going to talk about concurrency, because concurrency is related to all of this, and it's a really hot topic nowadays, and everybody has his own opinion, and they think, they have a solution for that. And different implementations approach that differently. And finally, we'll talk about memory management, because memory management, we don't have to do it, but somebody does it, which is the implementation. And if you don't understand how that works, you might not realize you're doing something wrong, or you might not realize the arguments for a solution against another one. So let's get started. Oh, before we get started, this is Ruby 1.9 only, and it's actually MRI. So I will quickly mention other implementations, but I'm going to focus mainly on 1.9 with some discussions about what changed. But it's really 1.9 only. If you're still using 1.8, I'm sorry for you. It's time you move on. So it might sound very boring to you. Yes, it might be boring. My goal is to make it less boring. If it's really boring, you have Café du Monde over there, and you can get a good coffee with beignet. Or you can just wait a little bit, go through that, and then you can think about what we discussed. So let's start at the beginning. We have a lot to cover, so I'll try to be quick. So let's see what happens. I write my own source code, and it's just a simple hello world. What happens when I write this code? Well, what happens is that first there will be a tokenization process. What that means is we're going to cut this text that comes from the source code, and it's going to be broken down into tokens. And here you have a representation of the different tokens. Now, after the tokenization process, there's a lexing that will happen based on a grammar. And basically, this is how we will break down the source code into things that might make sense for somebody to interpret. So you can see how things are breaking down into smaller parts, and then as you can see here, I explain a little bit how that works. You have basically the line number where it starts, the column it's on, the type of token, and the token itself. So once we have that, the parser can do its job. So it will take this Lex representation, and then it will convert that into an AST, which is an abstract syntax tree. And it's basically a bunch of nodes put together that explain how the language will be executed based on the grammar that was defined. So here we say we have a program that starts, we have a first command that's a POTS, and it's on a column 0, line 1, yes. And then we have, we're going to pass some arguments, and it's a string, blah, 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 and you can see all the information. Now, this AST is a representation of the program. Now, it's not enough to do much, but it's enough to have the language being defined. So this is implemented in MRI using a lexer and a parser, and you can actually go and look in the source code and see how that works if you're interested. And you can see how the language is basically being explained. And between the different Ruby implementation, that's what's really shared. Everybody shares the same approach to parsing the source code. So if you want to look at how it works in Ruby, you can actually use Reaper. And Reaper is a nice tool that was provided in Ruby 1.9 that allows you to see the underlying lexing and parsing that's being done. And Ruby MRI uses Lex and Bison, but with Reaper, you can actually have an idea of how that works. So you can take your code and look at it and see the end result. There are also some smart people that did the other way around, where at the end, I basically generate an the NAST. So the AST I showed you here, this is actually an S expression. That's not really how it is inside Ruby. But you can actually take this AST, modify it on the fly, and evaluate it. But anyways, this is how you can play with the AST to understand the language better, see how that works, see how Ruby interprets your code. Now, once you have this AST, you have the virtual machine that will do two things. So this runtime of virtual machine would do the compilation and the interpretation. And the compilation, and the virtual machine was written by Koichi Sasada, who's here, and I'm sure you know him. And it was replaced in 1.9. Are you here, Koichi? Maybe he's not here after all. Oh, sad. But he did a great job, and he's still doing a great job. So the compiler, the job of the compiler is to take the AST we saw and to compile it into a bytecode. And a bytecode is a representation, optimized representation of the AST. Now, once we have this bytecode, we can actually interpret this bytecode, and we can execute it by running it, and that's what's basically going to run your program. So this VM also handles the concurrency and the extension libraries, and we're going to talk about that in a minute, so don't worry too much about it for now. So the VM implementation, you have a bunch of C files. I would recommend, if you're interested in that, to look at the code and see how it's done. It's not really easy if you don't know C, but it's really, if you want to become a better developer, I would encourage you to learn a bit of C. It would just make you better. You don't have to be a C expert, and you don't have to contribute to MRI core, but I think it would really help you understand a different world of programming. So these are the rest of the VM files. Now, to understand how an implementation of Ruby works, these are the different parts of Ruby implementation. You have the garbage collector, which is what's going to manage the memory, and we're going to talk about that again in a minute. Then you have the built-in classes like hash, array, base object, all these classes that exist. Then you have the standard libraries like net, HTTP, OpenSSL, all these standard libraries. Then you have the string encoding, transcoding, which was modified for 1.9, which is very, very important because it allows us to deal with different type of encoding, like UTF-8 versus ASCII or binary encoding. Then you have the regex engine, which is what allows us to use a regular expression. You need to realize some languages don't have regular expressions, and it can be a pain. Then you have a bunch of small utilities that allows us to debug how things are working inside, to do time formatting and things like that. Then you have the parser, and then you have the VM. So this is what makes a Ruby implementation. So let's talk about C extensions, because they're really critical to the discussion, to everything else. Interestingly enough, you can hear people say, well, we cannot change this because of the C extensions. We don't want to break them. Well, what does that really mean? Well, we first need to understand what a C extension is and how it works. So C extension is usually used when you want to wrap an existing C library. So you can think of Nokogiri or the MySQL gem or a lot of different C extensions that actually have C code, and then they expose this C code. It could be used for performance, but usually it's because people reuse libraries that already exist, already perform, that you don't want to rewrite. So how does it work? Well, in C, you can actually define objects in the Ruby world. So this is some code I took from Aaron Nokogiri. And you can see it declares a bunch of values, and then it will use the C API that's provided by the Ruby headers, and it can say, Ruby, define a module called Nokogiri, and assign that to the value. And then I also want to define another module underneath Nokogiri, and then I would define another module underneath XML, which is under Nokogiri. And then you can see another example of the C API where we define a constant, and we'll set it inside a different module. So this is how you write C extensions. That seems pretty easy. Now, the problem is you also need to expose C functions. So a C function, it's not really, really hard. You can see we're doing the same thing. We're basically creating a module. In this module, we define a singleton method, and this method points to a function that's being defined underneath. So whenever we're going to call bonjour on RubyConf, it's going to call this C function that's defined underneath, and this C function returns a Ruby string. So that's a C extension. Now, if you stop here, you think, well, OK, so what's the big deal? Well, the big deal is that usually what you do, you would actually wrap structures in C. And for that, that means you need to manage memory. Now, that means you need to understand the garbage collector, because you will create object in Ruby that will wrap structure in C, and you need to make sure you don't leak memory, and you need to make sure things work properly. So when you define a class, in this case, I took that from the MySQL 2 client. When you define the class, you need to say, when my class is allocated, this is what you're going to do in C. And you're going to allocate a few things. And then we have the C function that basically defines how the memory is allocated. And you can see that the author first defined a value object. Then we have a pointer to a wrapper. It's a data type in C. We don't really know what it is yet. And then you have this line that says data make structure. And this is basically how, in a C extension, you're going to create a class or an object or whatever you want that will point to your own object in C. And when you do that, you will say, hey, Ruby, by the way, when you will run the garbage collector, please run these other functions for me so I can maintain my own memory and we don't leak memory. And what's interesting to see is this data structure has a name, as everything else, has these different functions, and then it has a pointer to the data, which is the wrapper we define above. And you can see then the wrapper is being set, all in C, and then some memory is being allocated directly to this wrapper object, and then we return the new Ruby object that was mapped so Ruby can use it. So what happens is when the garbage collector will go through, and it would want to check if the object is being used, it will call one of this function, which is RB MySQL client mark that was defined here. And here, we'll check if this object that we're pointing to still exists. And if it does, we're going to mark it to say it's a live object, don't do anything about it. And if the memory needs to be cleared, so if we need to free the object, in this case, we're going to call the C code and say, hey, by the way, get this wrapper, close this object, which we need to define, and that will free the memory that was allocated down here, almost at the last line, and then also free the pointer that we defined. And that's how we free the object. So you can see it's actually not that easy, and there's a lot of work to do to maintain the memory because the C code has to work with Ruby itself. So it basically, you have a few challenges when you write C extensions. You have to deal with the memory and the fact that you have the garbage collector to deal with. You also have to deal, which is a problem with C and any C classes, you need to make sure your code is cross-platform. So we have a tendency as a Ruby community to target mainly Unix, but a lot of people really work hard to make sure Windows work. And when you write a C extension, that's part of the challenges. And then you have the problem of thread safety, which is not a problem with MRI because we're going to talk about that, but basically thread safety, a C extension cannot run on multiple threads at the same time, so you don't have this problem. But I'm going to get to that in a minute because that's the next topic. Let's talk about concurrency. So concurrency is a big deal. Everybody wants to be concurrent. We all want to run a lot of code in parallel, and I just want to explain it a little bit by showing an example. So we would like to handle a lot of requests, web requests at the same time, and I will write a bit of Ruby code just to show you how that works. just to illustrate the concept of concurrency in a very simple way. So we have a simple client. We have a dummy client. And this client is a class with two functions. One is make a query. The other one gets the reply and will print the response that will come back. In the query method, we call the server and we dispatch ourselves with an ID. I mean, it doesn't matter how the client works. It's just to show as an example. Now, the server implementation, that will be a very simple server. It's a module with two functions. One is dispatch, which gets called by the client, and it would take the client and call reply on it, and it would pass a response, which is a fake response. And in this case, what I did is my fake response will be random, and it would take more time if the ID is odd than even. So, and my point is, I will show why I did that in a minute. So if we start 10 clients and we make them query the server 10 times, we'll see the response will come back as response 0, 1, 2, 3, 4, 5, 6, 7, 9. It's 8, 9. So they all come in a sequential order, which is not good because, as I told you, some of the responses will be slower. And if they're slower, that means that the one that's faster behind will have to wait for that. And that's not really good. The throughput really will be low because it will depend on the queue. So if you only test one call, you will always get the same speed. But if you make a lot of calls, you're going to have a different response time. So the problem with this approach is that it cannot scale as you get more load. So everybody will tell you, well, this is not a good solution. So let's use threads, because that's what we all know. So let's talk about threads. So what's a thread? Well, a thread is very simple. It's basically a code that gets executed in parallel and shares the same memory as everything else. So we have a main thread, which will be your Ruby application, and then you can branch that and say, hey, I want to run this code in parallel, and you can do that many times, and you can share the memory. So that sounds really good. We could rewrite our code to make it into a threaded server. So the only thing you need to do for that is I need to wrap the dispatch function body inside a new thread. And now if I query 10 times, I will see that the response come back in a different order because the faster response will come back before. That sounds really good. All right, so the 3D response will allow us to get a better throughput because it will not depend on everybody else on the queue that's before that. Now, there's one problem is if we have too many threads, we can actually slow down the server, and we're going to talk about that really soon. But threads are not magical. There's not something magical that just say, hey, when I have threads, I can execute all my code in parallel. That's just magical. The reality is that a CPU can only execute one instruction at a time. So there's something happening behind the scene to do this thread work, and that's called context switching. So context switching, it's not actually true. The OS is not always in charge, but context switching means you go from one execution code to the other, and you go back and forth. It seems like it's concurrent. You don't really see what's going on. I mean, you run a bunch of applications on your computer. They don't seem like they're running one after the other, right? But the CPU can only handle one thing at a time. It just switches back and forth. Now, when you do a thread context switch, which is basically when you switch from one thread to the other, it's still faster than when we switch from one process to the other. Finally, the context switch happens per CPU. So if you have two CPUs, you should be able to run two code exactly at the same time in parallel. So this is an example of how the schedule works in Ruby, in MRI. So that's Ruby uses a fair scheduler, which means that it will go back and forth between the threads with a time slice of 10 milliseconds. So we say 10 milliseconds on one slice, 10 milliseconds on the other slice, 10 milliseconds. Now, there's one thing, and I think that's a lot of people got confused about that, and especially because it changed in 1.9. What happens if you have a thread and there's a blocking operation? Are we wasting the rest of the time? Well, no. What happens is when you have a blocking operation in a thread, the thread is not being called by the scheduler anymore. There's no polling to check if the thread is still blocked or not. What happens is the other threads are going to be scheduled, but the OS on a native thread will come back and say, okay, my thread is back from the blocking operation, schedule it again. So this is how the scheduling works. Now, there's a lot of discussion about green threads and native threads. Ruby 1.8 used to have green threads. Ruby 1.9 has native threads. Ruby News has native threads. MacRuby uses native threads. What's the big deal? So a green thread is basically a thread that's handled by the runtime itself. It doesn't go to the OS and basically has one thread, and it would do the scheduling itself. So the pros of a green thread is that everything is managed by the VM. So it should be technically cross-platform. At least you get a unified behavior and control at the VM level because you know exactly how the threads will work. You also get lightweight threads because you don't have to use the native threads. They're lighter to start, they're faster to start, and the memory should be, in theory, smaller. Now, there's one major problem, is that it's not concurrent. So you're limited to one CPU. You have one thread, and that's it. You can only use that. So it's a big problem if you want to use multiple cores. And also, if you have a blocking I/O within one of these green threads, the other threads cannot run. They basically are blocked. So it seems natural that 14 years ago, when we only have one core, that was not a big deal. It was actually probably a good idea to use green threads, and that's what Matt did, and it was a good idea. But now that we have multiple cores, native threads are actually quite interesting because they allow us to run on multiple processors. They also get scheduled by the OS, so you have a bit less work to do. Now, you do have a lot of work to do because different OSs work differently, so threads are implemented differently, but at least you don't have to deal with some of the problems. The other thing is a blocking I/O happening on a native thread won't block the other threads, so that's good. So the problem with threads in general, not just native threads, is that you need to communicate between these threads using a shared memory. What that means is you need to use mutexes and locks because you have this shared resource and you have two people trying to communicate and modify them. You don't want that to happen, so you need to put a lock around that would say you can access it, then when you're done, the other person will access it. And that's actually a lot of work to do. If you don't do that properly, you can actually corrupt the data because you have now two threads accessing the same data structure, modifying it, and you have data corruption happening. You could also have deadlocks. You have your lock, somebody came to it, it never released the lock, everybody else wants to access the data, you get contention, you get a lock, and you're in a bad situation, and Java developers will know it's not fun to deal with. So it also adds a lot of code complexity because you have to worry about all these things, and that's kind of the challenge with threads. Also, if you have too many threads, you have to do context switching, and you saw how basically you have to go back and forth. If you have more threads, it's a bit complicated to explain because it depends on the system and how it's being used, but if the amount of threads is not appropriate, the context switching will be quite expensive. Now, context switching on native threads is much faster, as we saw than on a green thread. Finally, you get undeterministic behaviors with threads, which is a bit scary sometimes. 1.9 also added something else, which are fibers and continuations, or they're called both ways. What that means is actually very, very, very simple. People seem to be confused, but if I go back to my graph here, the schedule will switch between each thread. When you have a fiber, it's not the schedule doing that, it's you as a developer. So you say, start this fiber, this light thread, and then you tell it when to stop and when to come back and do it again. So basically, you're handling your own scheduling on your own thread with a bunch of fibers. It doesn't really help with blocking IOs, but it could help if you don't need to go back and forth between the threads because you know it's going to take a certain amount of time. It's also a bit lightweight, so it might save you on memory. So these are the fibers. So the big question is why threads are not popular with Ruby developers. And there are a few reasons. First, we used to have only green threads, and people thought, well, it's not worth it. Then we had a history of a lot of blocking C extensions. So if I go back again to my graph, you see when I say blocking I/O, the thread gets basically taken off of the scheduler. Well, when you do the C extension, you actually need to tell, you need to write in the code, you need to say, hey, this is a blocking operation, and I want you to do it in event. It doesn't matter. You need to do something, and that will let go. If you don't do that, then it would actually block until the end of the 10 milliseconds before it would switch back to the other thread. So we had this issue with some C extensions that were not doing that, and that was fixed. So that means that blocking IOs should not happen with DB drivers and other type of code. Now, the other issue was Rails. Rails until Rails 2.0.2.3 was not thread safe, which meant that if you were using threads, you would have really weird behaviors. And even to this day, if you start a new Rails project, by default, it would use a big lock around every single request. So it's not going to handle all the requests in different threads. There's also a lack of knowledge and understanding. People are a bit confused sometimes about what's going on with the threads. And finally, we have a lot of multi-core machines. Now we actually want to take advantage of the different cores, so we want to use threads. Now there's one problem, that's a big problem, that Dr. Nick loves to talk about, which is the global interpreter lock. So what is this GIL that people are talking about? What does it mean? Why is it so annoying? Why do people hate it? Why did Matt put a GIL in Ruby to start with? Well, the global interpreter lock is actually something very simple to understand. To avoid data corruption, and for the reasons I'm going to address in a second, every single thread can talk to the VM one at a time. You cannot have two threads talking to the VM at the same time. So if you remember the bytecode, when the bytecode is interpreted, you can only have bytecode from one thread being interpreted at the same time, just to make it simple. So that's really not a problem if you have one CPU, because anyway, the CPU can only handle one instruction at the same time. The problem is if you have more CPUs. So if you have two CPUs, you can still only handle one code execution at a time. That's kind of a problem. It's not really concurrent anymore. So the reasons why there's a global interpreter lock is first to make developers' life easier. It's really harder to corrupt data because you don't have access to the data at the same time. It's also to avoid race conditions with C extensions. The C extension level, it's much easier to find the race conditions, and I'll talk about that in a sec. So you make C extensions development much easier because you don't have to, if you don't have a global interpreter lock, you need to write a lot of code around your C code to make it thread safe. And if you ever wrote a Python extension, for instance, a C extension, you know that the C API is much harder to use, and you need to do a lot more work. And if you don't do it right, you're going to have a lot of problems like memory leak and data corruption. Most of the C libraries out there that people are wrapping are not thread safe, starting with the regular expression engine that's used on C Ruby. Now, there's another big problem, is that parts of the Ruby implementation itself, like the hash implementation, is not thread safe. And that means that if we remove the global interpreter lock, we need to go back and fix all these things, which will create some problems like making Ruby itself slower. So should we remove the GIL? And that's Dr. Ni's big question. There is a lot of implementations who don't have a global interpreter lock. So should we remove it in MRI? Well, there are a few answers, and I'm not gonna argue one way or the other. I just want to expose to you what the arguments are so you can understand. Well, first, if we remove the global interpreter lock, it will make Ruby code unsafer. It's actually, it is a fact that you need to understand how data works, otherwise you're going to corrupt the data. You also need to worry much more about mutexes and locks. If we do that, it will break C extension. And that's something people hear all the time, and like, so who cares, right? You always tell me, Dr. Nick, like, oh, I don't care. Like, let's rewrite all the C extensions, you know, who cares? Well, you didn't say that, okay. So last night, okay. Yes, that's correct. He never said that with my accent. It was more with an Australian accent. So, well, the C extension, as I showed you at the beginning, if we would remove the global interpreter lock, it's not as simple as changing the way we have the C API and just the way the calls are made. We actually need to change the way memory is handled and the way you need to handle a lot of the challenges at the C-level extension, unless we actually make even more changes so C extension will be compatible. But that's a big one because it's not as simple as just doing a find and replace and then we're good. It would also make writing C extensions much harder. So for instance, depending on the solution that's being used, you need to use write barriers. And there's a lot of work that would need to happen at the C extension layer to make these things happen. It was not you, I know. Oh, anyway, let's move on. It's also a lot of work. So that might not be a good argument for a lot of you. It's like, well, who cares? Just do it. That's actually what Dr. Nick was telling me yesterday. Right? Do you agree with that? It's too much. Let's just do it. That's what you were saying. No? I think we should have a go for Okay. So it's a lot of work to go in implementation and change it. When you have a new implementation, it's much easier, but going back will take a lot of time. You can actually break a lot of things, and it's a big, big change that might or might not be worth it. A lot of the Ruby applications out there actually are not affected by this thing. They're not CPU bound, and they can deal with other workaround of that. I believe that most people could deal with the global interpreter lock. Python users have been dealing with that. We've been dealing with it. It's not the best situation, but it still works. It's not the worst case in the world. And a lot of people would say, well, instead of focusing on this concurrency issue, why don't we focus more on the memory usage, on the garbage collector, all these things that actually slow down also Ruby that could really improve without having to break the C extensions, without having to break the way things work, and without putting the Ruby code in danger. Also, as I mentioned earlier, if we remove the global interpreter lock, we would have to go back into the C code, into MRI, and we'd have to make sure everything is thread safe, and it would make the C code just run slower. So what are the arguments for? Well, first, we really need better concurrency. I think that's the main reason. We really want concurrency, so that's a good argument. The other argument comes from the Python community, and they have this analogy of the rubber boots, and they're saying, well, it's kind of stupid to wear rubber boots every day and to deal with that just because it might rain. Well, the reality is, even if it rains, not everybody will be outside in the rain, and boots will not solve all the problems in the world. So maybe we should not pay this price, and we should just deal with the real challenge of working with threads. And that's the approach that some people are taking. So these are basically the arguments. I'm sure you can hear other arguments, but these are the main arguments you'll hear. And this is probably why MRI is not going to lose his global interpreter lock right away. So how do you achieve concurrency if we keep this global lock? Well, you have multiple ways. The easiest one is to say, well, let's start multiple processes. If you have multiple processes, each process can work on one core, and then the threads will basically use the core. We're good to go. The problem with that is it uses twice the amount of memory. It's not that great. Well, what you could do is you could fork the process, which means you start the process, you fork the process, and then now you have two processes, and they can basically share the same memory. Well, actually, I'll make it simple. You start the fork, and the fork will not need to copy the entire memory into the fork. That sounds good. The only problem is that MRI is not copy on write friendly, which means that, or the garbage collector of MRI is not copy on write friendly, which means that when you fork the process, you don't have a lot of memory used in the fork. But when the garbage collector will come, it will go and check on all the objects, and basically the memory will increase to be exactly the same amount as it is on the master process. And that's why Ruby Enterprise changed that to, they changed the implementation, they patched the garbage collector to be copy and write friendly. So now you only deal with the allocation done on the fork. Now, Ruby MRI is actually going to fix this problem. They've been working on it for quite a while now, to have the bitmap marking a GC. So what that means is, instead of marking every single object, what will happen is that they will keep a bitmap, like a big table of all the different slots, what's being used, and you have the marks being used, being put here. So when you fork the process, this bitmap is being copied over to the fork process, and now when the garbage collector would run, you don't have to actually double the memory, or basically get the entire memory same as master. So that's going to be fixed. There's already a patch for it, and it's being worked on. So already might be implemented in 1.9.4 or 2.0, so that's coming hopefully soon. Then you can do evented programming, which is done, for example, using even machine or something like that. You can use the messaging actor model, which is an interesting approach, and a lot of people are talking about that, where instead of communicating by sharing memory, you communicate by sending messages between different objects. And this way you can get better concurrency. And then the approach that Koichi-san presented for the future is to run multiple VMs. And the way that would work is that within the one process, you would have two VMs, if you have two cores, for instance, and each VM would talk directly to its own core, and now you actually you get the full concurrency, even though you get a global interpreter lock on each VM. So that's one way of solving the problem. So let's talk about memory management, because it's also related to all of these issues. So when object allocation happens, every time you declare an object, you actually allocate something. So this is an example. If you say 100 times a string, it would actually allocate 100 strings in 100 string objects. If you create a hash, that would actually create 4 objects. You have a hash, you have the 2 values, and you have the key. If you define a class and you create an instance of this class, that will allocate 1 node, which is basically the code itself of the class. Then you have 2 classes, probably the class and the singleton class, and then you have the instance object. So the garbage collection prior to 1.9.3, so basically everything that's now released, so 1.9.2 and everything before, that's the way it was working. You had memory, so that's the Ruby heap. We have basically a bunch of slots. The ones that are dotted are the ones that are live objects. They're marked as being objects that are being used. So think about a variable that's actually being used inside your code. You cannot get rid of it right away. And when you try to allocate a new object, we'll get from the free list, which are the available slots that are here available in the Ruby heap. That works great. So what happens if you don't have an available slot? So if free list is empty, the garbage collector is being called, and the garbage collector will come and will, do I have a slide for that? We'll go through the list and check every single object, the entire Ruby heap, and say, are you free or are you live? So it goes and works through all these objects until it will mark each of them. So it goes to an object, say, are you live? If the object says yes, it will mark it. If it doesn't say anything or if it's not sure, it won't mark it. At the end, it would basically sweep, so it would take all the objects that were not marked, and it would free them, and well, it would basically put them into a free list, and it will reuse this slot for the new object that's being allocated. So what happens if you go through the entire slot, and they're still used? You all have Ruby object. So what happens in this case, the garbage collector comes, goes, scans everything, all the objects are marked, you don't know what to do. Well, the garbage collector cannot find anything to reclaim. It will allocate another Ruby heap with more space. And this slot now can be used for new objects. Now in 1.3, things change. And this is quite important to understand because it would really affect performance in a lot of your applications. So this is what happens. You want to allocate a new object. We have a free list. It will take the object, the same as before. Now what happens if free list is empty? Well, if free list is empty, you want to allocate a new object. There's no free list. In this case, the garbage collector would just take one row and would mark it. And it will go through and find the objects that are used. If they are not used, it would swipe only this row and use that to allocate the new object, which means that the garbage collection time will be much, much faster because it doesn't have to scan everything. So what happens if there's still nothing at the end of if you basically go through all the rows and there's still nothing, what happens is we do the same thing. We allocate a new Ruby heap to get more space. So what you need to understand is with this approach, we might run the garbage collector a bit more often, but the time spent in the garbage collector will be much smaller. Which, if you run some benchmark, and I did on some of my applications, you actually see quite a lot of performance improvement depending on your application, obviously. So there are different types of garbage collectors. You know, we hear talking about the conservative garbage collector, like the Tea Party, it's like the awful garbage collector, but you have the precise one. That sounds like that's the good one, right? But how come Emerald doesn't use a precise garbage collector? Well, in the case of CRuby, the garbage the garbage collector is a conservative garbage collector. And the reality is, if you use a C implementation, you have to use a conservative garbage collector. That's the case also for MacRuby. And the reason for that is because you deal with pointers, and you don't always sure if the pointer to object, what it points to, and you're also not sure about the length of the arrays. So using a conservative GC is actually normal. Now, the CRuby is a stop-the-world garbage collector. It's the same thing for Ruby News. What that means is when the garbage collector runs, nothing else can run at the same time. So everything is stopped while the garbage collector runs, which is why it's important that the garbage collector doesn't run for too long, because in the meantime, nothing happens. So the lazy sweep allows the stop-the-world to actually be shorter, so that more code can run at the same time, which is can run within the same time. And then it's a lazy sweep, which I just explained, which means that the time spent in the garbage collector is now lower than it was before. So if before you would run the garbage collector, it might take, I don't know, let's say 20 milliseconds, which is quite a lot. now it would probably spend only 2 milliseconds, but it would run more often. So the time spent in the garbage collector overall within your program will be the same or maybe even longer, but the time spent every single time will be shorter. So we have other examples of garbage collectors in the Ruby world. We have the case of MacRuby, which I work on, so I know it a little bit. It's a multi-threaded generational GC. So what does that mean? Well, that means that in the case of MacRuby, we run multiple VMs, and we don't have locks. They're multi-entrant, re-entrant VMs. And they don't have locks. The lock happens in the core, which is, I'm not going to explain that right now. But the GC runs on a different thread connected to the VM, and every single thread registers to the GC. Generational means that objects are organized by time that they've been spending in the garbage collector or in memory. So you have the youngest objects that get allocated in one place, and then you have the young object, which the ones that survive a few GC cycles. And basically, your data is organized in different ways depending on how long it lives. And the reason why it's done like that is so the first generation, usually this object are being allocated and they're allocated right away. So you want to have them in one place. This is also the case for Rubinius, which uses a generational garbage collector. The difference is in their case, because it's a precise garbage collector, and I will explain that in a second, they can actually move the object from one memory place to the other. So Rubinius uses a stop-the-world precise moving generational GC. So stop-the-world is the difference with MacRuby, where MacRuby does the garbage collection in the side. Rubinius stops the world. It doesn't stop it for a long time, so it's not a big deal, but it still stops the world. It's precise. What that means is that unlike CRuby, the implementation itself handles all the objects and knows exactly what's going on with all its objects. So it can actually, it doesn't have to guess, it doesn't have to be conservative. And conservative, I didn't really explain what it is. Conservative is instead of, when it's time to mark and release objects, what it will do is, if it's not sure, it will basically keep the object in memory. In the case of a precise garbage collector, we know exactly where, how the memory is allocated, so we can actually take care of that. We can even move the object in memory. So also because it's precise, which I just explained, you can actually move these things. It avoids fragmentation because as you remove slots, they don't always have the same size. You want to allocate a new object, they might not fit. By moving things, you can actually allocate the memory in a better way, and you will avoid fragmentation by quite a lot. Potentially, Rubinius could also release the memory that's not being used. So let's say you allocate a lot of objects, the memory grows a lot, and then you actually end up not using that much. Rubinius could clear this memory, so you would see the usage going down when you use MRI. Once you hit 100 megabytes, which probably is what happens when you start Rails, you will never go down. So you have another type of garbage collector, which is the reference counting, and this is what's used by CPython and other solutions like Objective-C on iOS if you don't use garbage collector. Well, on iOS you don't have garbage collector yet. So each object will keep track of its state. What that means is I create my object and I will tell the garbage collector this is who depends on me, this is what I do, and you will keep on counting what's going on, and when it's time to be released, the object itself will basically say, hey, I'm free to be deleted. This is great because it's decentralized. So you don't have one place that deals with that, every single object do that. The problem is that it's really hard for everybody else because now C extension developers need to do that for every single allocation they do. You have a lot of opportunities for memory leaks and for a lot of other problems. You also have the hybrid solution, which is the case of the JVM, and I'm not really familiar with the details of the JVM, but the JVM first is a VM that you can configure when it comes to the garbage collector, so you can decide how you run a garbage collector. But what it can do is it can be generational, like we explained before. It can also do the occasional mark and sweep, where it goes through the entire memory. And it can be copying the data, and copying the memory, which I will not explain now because I'm running out of time. So what are the tricks? Well, there are a bunch of tricks, and the MRI team is working on a lot of things to try to optimize garbage collection. Lazy sweep was one step, but they want to do much more than that. So the bitmap marking is what I explained before, and that allows for better forking. which means that if you start, let's pretend you start one Rails app and you have the same code, you could fork this process and have 2 or 3 other Rails apps, and it would not be 4 times the cost of the memory. You would basically share what was loaded at the beginning. And if you use Ruby Enterprise, that's exactly what you get. Then there's the parallel marking, which is every single thread would basically talk to the GC and would mark its own object in every single thread. It still stops the world, but it's done differently. Nadisana did a talk on that. You can see his slides online if you missed it, or you can watch the video when it will be released. Then you have the mostly copying GC. So the mostly copying GC, what that means is that in memory, the problem is fragmentation in this case. That's the problem you're trying to solve. So the problem is we have this object, we allocate, we deallocate, and when you have this new object, they don't always fit in the old object spaces. So what you do is you copy the memory, and you basically copy the object that you know are safe, and you move them somewhere else so you can reallocate the other ones. The problem with that is that you end up using more memory, but the fragmentation issue almost goes away. Then Twitter did his own tweaks on the garbage collector, and you can read it online. There's a link on my slides. Basically, they did a few things related to what the Ruby Enterprise Edition did, plus they applied some sort of long-life GC patch, which means that it's almost generational. So they look at the objects that are here for a long time. So when you start Rails, you load a lot of code and a lot of objects that will never go away. So what they take is they take this object, they put them in a different place so they don't get garbage collected or not as often. There was a long-life GC patch that was almost applied to 1.9, but it turned out it was not the best solution ever, and Matt can explain that more in details. They're really working on the GC, so if you have the opportunity to talk to them, I'm sure they would be glad to explain. Then the last thing is something that was in Ruby Enterprise, and that's back in Ruby 1.9.3, so GC tuning. And the GC tuning allows you to set a lot of settings on the garbage collector, and you need to understand a little bit how that works. But by doing that, you can make sure the garbage collection usage is optimum, so it will go faster. So what's the big deal with garbage collector? Why do I care that much, and why do I get upset when people allocate too many objects and I tell them they're making a mistake? Well, it's like if you have a car. If you have a car and it's a small car, let's say you have a small Fiat, and JLo is not in the car, and you want to do something with this car. If you put 15 people in this car, it's not going to go fast. So you need to think about the type of car you have. If you understand how things work, you'll be able to use code the best way you can. And the reality is, currently, the garbage collector makes things a bit slow. If you generate the RDoc, at least for Narisan, what happened for him is that he spends 80 seconds to generate the entire RDoc, and 30% of this time is spent in the garbage collector. At Twitter, in 2009, they did some tests, and they realized that they were spending 20% of the front-end CPU on garbage collection. I did myself some tests when I was working at Sony, and I was seeing the same number and sometimes even higher, depending on the quality of the code that was written and the amount of object being allocated per request. So there's a concrete effect on the performance of your code, especially with Rails, where a lot of objects are allocated every single request. You need to realize the cost of the garbage collector, because it would actually slow down every responses when you get a lot of requests coming in. And what you can do is use the tools that are provided to you by Ruby 1.9 to see how the garbage collection is being used. So this is a simple example to show you how that works. At the beginning of the code, you turn on the garbage collector profiler, and whenever you want, you output the result of the garbage collector profiler. And when you do that, it will basically show you all the different collections that happen, how long they spent, what's the total memory usage that's allocated for in memory, and what's actually used within this memory. When was it invoked when it comes to time? In the timeline of the execution, when was that executed? How many objects are available? How long did it take in milliseconds? Now, in itself like that, it might not be very useful, but you can use it with object space, which object space allows you to show you how the memory is being used, what's in memory. And here's a simple example where I disable the garbage collector to not get information. I didn't want an object to be freed. So I turn off the garbage collector. I take a reference, which is at this point in time, how many strings do I have in memory? And then I allocate 10,000 strings, and then I get the count, and I remove, well, I get the new count of strings, and I remove the reference, and then I will print the amount of strings. And you can see object space count object basically is a big hash representing the memory. The total is the amount of objects that are available. Free is the length of the free list, and then you have the allocation per object type. So this tool can actually really give you an idea of how the garbage collector is working and what you have in memory and what you're doing. And I wrote a very simple rack middleware to show how that works, to do some of the work I was doing to see the optimization of the garbage collector. So I wrote something very, very simple. It's not fancy, but it basically gives you that. As a rack middleware, it would run, at least when you enable it. And as the garbage collection will come, it would tell you the last GC cycle happened X amount of requests ago. 4 GC cycles were run, or 40 cycles in this case. And this is the amount of time spent for each of them. And you can see in this case, I'm spending 14, 15 milliseconds in the garbage collector. My goal working on APIs who had to be fast was to get a response time of 30 milliseconds. Anything above 100 milliseconds was really bad, and the goal was really 30 milliseconds. If I spent that much time in the garbage collector, I would have major problems. And at the end, I basically use object space to show you some stats about how the memory change happened between the last GC cycle and this GC cycle. So that gives you an idea of how the memory is used. And I would really want to encourage people to pay attention to this, to the memory allocation, because it really costs you a lot of time on request time. That's it. Any questions? Oh, yes, it's merbeast. I forgot the B. Thank you. Yes, it's the same as my Twitter handle. So I put the slides there in HTML. You can see them. Any questions? Nick, do you want to come and talk about your problem with the global lock? I kept it. So, any question? Okay, a question over there? Oh. No questions? See a question over there?
I do not believe the photo of Ghost was taken by Sam Wheat.
That was not a real question. You are absolutely right. I was wrong about that. The photo was not taken by the person I mentioned in the source. Any other question?
We've seen a lot of change in Ruby over the years, and Ruby core hasn't been afraid to break things in the past. So what makes the GC special that we can't just break things? I mean, look at the 1.8 to 1.9 transition. We changed a lot of how Ruby works.
So let me just repeat the question. So the question is, a lot of things changed in the past with MRI. For instance, the string and the encoding that broke, that changed things in 1.9. How come we cannot change the global interpreter lock? Is that what you're saying? Or the garbage collector?
What makes the GIL special is the sacred cow we can't change and break backwards compatible?
What makes the GIL special? Would you like to answer, Matt?
The main concern we have for GIL is not the compatibility, but it's the unsafeness. So if we allow the CRuby to crash when you use threads, we can remove the GIL. But I don't want the Ruby to be like that.
Thank you for answering for everything else.
Any other questions? That's it. Well, thank you very much, and see you next year.